Okay, so this last part of chapter 4, unit 4, is all about connecting f of x, f prime of x, and f double prime of x, which we've done some of this before, but it's just kind of like re-emphasizing it, and some of this will be new with the second derivative. So it says, let's begin by filling in the following charts about the relationships that exist between the graph of the function and its first derivative, which we should know this already because we talked about this already. Remember that when you set a function equal to 0, set its derivative equal to 0, right, where the derivative equals 0 or is undefined, remember that those are called critical points. And what do we know when that's happening? We know that if the derivative equals 0 or it's undefined, that is a possible relative max or min. What do we know when the derivative is greater than 0 about the original function? Well, if the derivative is greater than 0, that means the slope is positive, right? So what does that mean for our graph? That means that f of x is increasing. I guess it already says f of x, so I should just say then f of x is increasing. And when the derivative is less than 0, then we know f of x is decreasing. Again, this should just be like refreshing your memory here about this. And when we know the derivative changes from positive to negative, right? So it equals 0, and it changes from a positive, which means from increasing to decreasing, we know that that is a relative max on f of x at this point, right? And if it changes from negative to positive, the derivative, that means it's changing from decreasing to increasing. So that is a relative minimum at x equals a. So we've done this before. We made the little sign chart. So let's just kind of refresh our memory here and see what we can do. So it says, you have already seen this action with polynomial functions. For the polynomial function below, determine the intervals where the graph is increasing, decreasing, has a relative max or min. Show your analysis and justify your answer. Okay? So every time if we're trying to talk about relative max and mins, we want to take the derivative. So we would get 4x to the third minus 12x squared. And we're going to set that equal to 0. And right away I can see that I can factor out a 4x squared. So that would leave me left with what? X minus 3. And then I just set each part equal to 0. So if I set that equal to 0, I just get x equals 0. And if I set this side equal to 0, I get x equals 3. Now remember that those are my critical points, right? Critical points, which means possible max and mins. But I have to check to see what's happening. So that's where I make my little number line. And I check to see what's happening to the derivative, which is here, not to the original function. So I plug in a number to the derivative less than 0. So if I plugged in negative 1 there, 4 times whatever, negative 1 squared is going to be a positive, and then negative 1 minus 3 is going to be a negative, and so that's going to be a negative number, which means my function is decreasing. And if I plug a number in between 0 and 3, I'm just going to pick 1. Then I'm also going to get a negative because I'm still going to get a positive over there. And 1 minus 3 is still negative, which means decreasing to decreasing, which means 0 is nothing. And then if I plug in a number bigger than 3, I'm just going to plug in 4. I'm going to get a positive, and 4 minus 3 is a positive, which means that that is increasing. Remember that we don't usually say that it's decreasing at 0, right? So like if I was going to say this, I would say f of x is decreasing from negative infinity to 0 and from 0 to 3, because it skips over at 3. It's actually 0 at 3. F of x is increasing from 3 to infinity. And f of x has a relative what? Decreasing, increasing, relative minimum. At x equals 3, if we wanted to find the point there, we would have to plug that back into the original problem, right? We'd have to plug that back in there. I don't think that it wants us to do that. It didn't say give us the points, so I'm just going to say at x equals 3, and there is no relative maximum on this graph. If it said justify your answers, which it does, this chart that I showed is not sufficient evidence, if you remember. I would say f of x is decreasing because f prime of x is less than 0, decreasing because f prime of x is greater than 0, and relative minimum at x equals 3 because f prime of x changes from negative to positive on there. No relative max because it never changes, the derivative never changes from positive to negative, right? We've done that already. It says polynomial functions deal with critical numbers where the first derivative is set equal to 0. Since the initial investigation of these properties, we've talked about places where a function is not differentiable, like a corner or a cusp or an asymptote. It says that does not exclude the existence of relative maximum in. Let's investigate such a case now. We've looked at a lot uglier graphs since then, and so that's what we want to talk about right now is that part. So it says analytically find all the intervals where f of x equals x plus 2 to the 2/3 plus 1 is increasing or decreasing or has a relative max or min. Sketch a graph using a graphing calculator on the grid at the right to verify your results. So if I take the derivative of this, I'm going to bring down my 2/3, and I'm going to get x plus 2 to the negative 1/3, and then the derivative of 1 is just 0. Critical points are where your function's derivative equals 0 or is undefined. Polynomial functions, the derivative is never undefined, so we don't have to worry about any of that. But if you look at this and we move this down to the bottom, if you think about where does this equal 0, we talked about this, like to find where function equals 0, you just set the top equal to 0. There's no place that this function equals 0. But it is going to have a 0 in the undefined part at x equals negative 2 is undefined on f prime of x. So that is also a critical point. It means as long as it's defined in the original function, it could still be a relative max or a min, even though in the derivative it's undefined. And if you think about plugging that back up in here, you just get 0 plus 1, which is 1. So check on your graph. Even though you can't plug in negative 2 into the derivative, if you plug in a number left of negative 2, let's just say negative 3. If I plugged negative 3 in here, I would get negative 3 plus 2, which is negative 1 to the 1/3, which is still negative 1. So that's going to be a negative number. And if I plug in a number bigger than negative 2, I'm just going to pick 0 here. That's going to be just 2 to the 1/3. That's going to be a positive. So we can say that f of x is decreasing from negative infinity to negative 2 because f prime of x is less than 0. F of x is increasing from negative 2 to infinity because f prime of x is greater than 0. And we have a relative min at x equals negative 2 because f prime of x changes from negative to positive. What does that look like when you graph it? Well, you can get your graphing calculator here. But if you plug in negative 2, you get 1. And a 2/3 one, that's one of those weird like bird ones. I'm just going to really, really roughly sketch this. But it kind of looks, you can verify on your calculator, like this. That is not differentiable, but notice it does change from increasing to decreasing. And so it can still have a relative max or min. And so they kind of just summarize this down here. Whoa, that's not what I wanted to have happen. Goodness gracious. We'll just ignore that. It says the first derivative of a function identifies intervals where a function is increasing, decreasing, has a relative max, or has a relative min, right? That's what we've been doing this whole time with derivatives. Now, it says in a similar fashion, the second derivative, and we've talked about this a little bit, but the second derivative indicates where a function is concave up, concave down, or has a point of inflection. That's kind of a new part. And it says since the second derivative is the first derivative of f prime of x, we can also use this same relationship between f of x and f prime of x must exist between f prime and f double prime. And so we're going to try to see what we can do with this, okay? So I'm going to do a little bit more, and then we'll go from there. So it says, with these relationships in mind, complete the following table. Okay, actually, I'm going to stop.